In order to understand the structure of alkanes, we have to review hybridization, understanding where hybrid orbitals come from. And so we're going to make a model for methane. And um, this should be review for you. And I know that hybridization is discussed in general chemistry, but hopefully if you're not clear on hybridization, this can clear some things up for you. Now, where do we get the whole idea of hybridization? Well, it comes from physical evidence. So physical chemists tell us that methane is tetrahedral in geometry. And it has a structure that looks like this. So carbon has the four hydrogens connected to it, and those hydrogens are separated from one another as far possible, as far apart as possible. The bond angle is 109.5 degrees. And this geometry cannot be explained by the atomic picture of carbon. Why? Well, if we look at the atomic orbital of carbon, we see that carbon has in its valence electrons, they reside in a 2s and 3 2p orbitals, px, py, and pz. If we think about where those electrons reside in this atomic orbital structure, we know that two electrons reside in the 2s orbital. They are paired, and then two electrons reside, one in a px, let's say arbitrarily, and one in a py. So one in one p orbital and one in another p orbital. And then the last p orbital is empty. And if we draw a picture of this, so kind of getting a picture representation of this, we start with that 2s orbital of carbon, right? So that's the s orbital. And then we have the three p orbitals, so the px and the pz, right? And then the py is going to be coming out at us. So px and pz are in the plane of the board, and the py is coming out at us. So I'm going to kind of draw one lobe it's coming out, and another is a dash that denotes that it's actually going behind me. So that's the py. So in carbon as an atom, this atomic picture tells us that I have two electrons in the s orbital. I have one electron in my arbitrary designated px and one electron in the py, and the pz is empty. Now, what does this mean? In terms of forming a covalent bond with hydrogen, remember one electron comes from one atom and the other electron comes from another atom, typically. And so only two hydrogens can form bonds with two unpaired electrons, right? So the structure, carbon should be able to form a bond with only two hydrogens, and yet that is not the case. The other thing is that the bond angle would be 90 degrees, okay? And of course, we know the bond angle is not 90 degrees. In a tetrahedral, the bond angle is 109.5. So the question is, well, how do we explain the structure, the geometry of methane? Well, in order to explain the geometry, we have to actually combine the 2s orbital with one or more 2p orbitals and see what we get out of it, right? So I'm going to go through each possible scenario, right? And the first scenario is what we call Sp hybridization. So this is where we're simply taking a 2s orbital, right? Carbon's 2s orbital, and one of carbon's 2p orbitals. So remember, we have this picture where we have an s orbital and we have the three p orbitals. We're going to take the s orbital and only one of the p orbitals, and we're going to combine them together. Now, remember, whenever, this is similar to molecular orbital theory, where you're combining two atomic orbitals to make a molecular orbital. Well, in this case, you're combining two atomic orbitals and you're making two different atomic orbitals. So there is a little bit of difference, understand that, but the principle is the same. Whenever we take two orbitals and we mix them together, we produce two new orbitals. And so we get two sp orbitals. And then we're left with a py and a pz. Right? So we still have a py and a pz. So now we have, again, still four orbitals, but now notice the energy is a little bit different because the two sp orbitals are going to be have the same energy, and then the two p orbitals are going to have similar energy. So what do these new hybridized orbitals look like? Well, if we go back to that picture of a p orbital, so here is my 2px orbital, and I combine it with a 2s orbital. Remember, I can combine orbitals either in an addition way or a subtraction way. So if I first add the two orbitals together, the result is I get a structure that almost looks like a lopsided p orbital, right? The 2s has combined with the in phase side of the 2p orbital, and it's basically expanded that region and contracted the other region. And so this is what an sp orbital looks like. Now notice it has 50% s character now and 50% p character. And this will become important later on, especially when we think about how electrons can stabilize themselves in terms of penetrating into the nucleus, right? The more s character you have, the more stable it is. The more p character you have, actually the less stable it becomes because the electrons become farther away from the nucleus on average. Okay, so another combination is taking that px orbital and the 2s orbital and subtracting them from one another. And the result is now I've subtracted the blue area and I've enhanced the green area. And so this simply becomes another sp orbital. And so notice the two sp orbitals look very similar together, very similar to one another. Um, don't get don't get tied up in the colors, okay? Very important to understand that we're just representing the different phases as colors in terms of combining things together, but in reality both sp orbitals look very similar to one another. So we have these two sp orbitals, and then we still have two p orbitals that are unhybridized. Now, one of the cool things about hybridization is when you think about the overlap of an sp orbital with an s orbital, that overlap is much less wasteful than the overlap of a p orbital with an s orbital. Let me demonstrate. Here I have a p orbital, right? So let's say this is the 2px orbital that's not hybridized. And when I actually form a molecular bond, so I'm not talking about hybridization, I'm talking about, let's say I have a hydrogen 1s orbital or anything that has a 2s orbital. So I combine them together and I'm forming a new molecular orbital, right? The process simply, we get this overlap of the 2s with the in-phase area of the 2p, and I form a molecular bond. We call this a sigma bond, right? A sigma bond between a p orbital and an s orbital. Now, compare that to a hybridized sp orbital in its interaction and mixing with a 2s orbital. All right, so again, we're forming a molecular bond, and that bond looks like this. right? So you see that now the electron density resides a lot in the blue and much less in the green. So we say that green area is a wasted space, and in this overlap sigma bond of the sp to the 2s, there's much less area that's actually wasted. Now, one structure that can be explained using this sp hybridization is beryllium hydride. So beryllium hydride bonding is explained by sp hybridization. Why? Well, if again we think about the atomic structure or the atomic uh, um, symbol of beryllium, again, we have a 2s orbital, we have the three 2p orbitals, and beryllium has 2 electrons in its valence electrons, and therefore those 2 electrons reside in the 2s orbital. So in terms of predicting any bonds forming, we would say that beryllium shouldn't form any bonds whatsoever because it has 2 electrons that are paired up, so no unpaired electrons can exist. However, if you hybridize the orbitals, right? So taking this picture of beryllium, now I'm going to hybridize, get the 2 sp orbitals, and then my 2 leftover unhybridized p orbitals. And the sp orbitals are lower in energy than the p orbitals are, and so when I fill those orbitals, one electron goes into one of the sp orbitals, the other electron goes into the other sp orbital. Now I have 2 unpaired electrons that can form a bond with hydrogen. The other thing that we have to think about is geometry. So what does the geometry of an sp hybridized atom look like? Well, to minimize electron-electron repulsions, sp orbitals are as far apart as they possibly could be. And that would be 180 degrees because we have 2 orbitals, and so those 2 orbitals would lie directly opposite one another. So this gives us a linear structure, and we would predict atoms that have sp hybridization to have a linear structure. And indeed, beryllium hydride is linear, right? So now we can kind of draw a molecular orbital picture of the entire beryllium hydride. And we're going to start by simply thinking about how beryllium and hydrogen form a bond, right? So we start off with hydrogen's 1s electron, the energy of hydrogen's 1s electron, and the energy of the beryllium sp orbital. Now, in reality, this would be a little bit higher in energy, right, because it has some p character to it than the s orbital, and of course it also has a higher principal quantum number. But for simplicity's sake, I'm just going to put them at a relatively equal value, but understand they are not equal value. And so now I can draw my energy diagram, and I say, because I know that when I mix 2 atomic orbitals, I get 2 new molecular orbitals, right? And of course, the bonding molecular orbital is going to be from the overlap of the sp with the 1s electron. So that's what this particular structure looks like, and then overlap looks like. And then the anti-bonding orbital is where the sp anti-bonding orbital combines with the 1s orbital in a manner that are out of phase with one another. And we form that node, remember? Now, we call the bonding an sp plus a 1s and the anti-bonding an sp minus a 1s. But in reality, we don't call them those terms necessarily. What we call them are sigma bonds and sigma star bonds. So when we look at where the electrons are going to go, we have one electron from hydrogen, one electron from beryllium. They combine to give us our bonding or molecular orbital, which we call a sigma bond, right? Sigma bond. And the antibonding orbital is called a sigma star bond. Now, that is one beryllium hydrogen bond, molecular bond, right? And it's a sigma bond. So looking at the entire structure, we know beryllium has an sp orbital that bonds with 1s orbital of hydrogen. It has another 1 sp orbital that combines with the 1s orbital of another hydrogen molecule. And there are 2 electrons that reside in each orbital. That is what we call a cylindrical bond. And a cylindrical bond is what is referred to as a sigma bond. So there is no change if we rotate about that bond. There's no change in that bond, which we'll get into a little bit later. And of course, also recognizing there is also an empty pz orbital, and there is an empty py orbital. So this gives the biggest representation of beryllium hydride, linear, showing the 2 sigma bonds that exist. Now, that obviously is not the model of methane because methane is not linear, it's tetrahedral. So let's move on. Another way that we can hybridize is to combine the 2s orbital with 2 2p orbitals, and this is called Sp2 hybridization. So again, we look at our atomic model where we have the 2s and the 3 2p orbitals, and we're going to now combine the 2s with 2 of the 2p orbitals, right? And the result is, since we're combining 3 orbitals, we get 3 orbitals out of it. And those orbitals are sp2, oops, sp2 orbitals, right? So draw those in there, 2 and 2 and 2, right? Now we have sp2 orbitals, and we have one remaining pz orbital, right? And of course, again, z is an arbitrary value, arbitrary direction of the orbital. And now notice in the hybridization of the sp2 orbitals, we have 33% s character and 67% p characters. We're gaining more p character, but the orbital picture is still very similar to an sp orbital, so it looks the same as an sp orbital. Now, instead of having 2 hybridized orbitals, we have 3 hybridized orbitals. So when we think about minimizing electron repulsions, these orbitals align themselves in a trigonal planar geometry, right? To minimize electron repulsions of essentially 3 electrons in those p orbitals, it becomes trigonal planar geometry. So to represent that, I'm going to look as the orbitals would be in the plane of the board, and I'd have these 3 sp2 orbitals, right? Understand that they are planar. What does that mean? That means they are flat, right? They are all in the plane of the board, and the bond angle is 120 degrees. Now, if we look at the side view of that, then we can show that I have one sp2 hybridized orbital in the plane of the board. I have another one that's coming out at me, so I've drawn a kind of a wedge-y looking orbital, and then a dash that's going behind me, right? So here I have my 3 orbitals, and now they are perpendicular to the plane of the board. And then, of course, I have my empty p orbital that exists as well. So I have an sp2 orbital here, an sp2 orbital coming out at me, an sp2 orbital going behind me, and my pz orbital that's left behind. Now, we would expect the bond angles to be 120 degrees, so obviously methane doesn't fit this hybridization as either, but BH3, boron trihydride, fits this geometry. So boron has 3 hydrogens surrounding it. It is trigonal planar geometry, and it has an empty p orbital that exists. So the last type of hybridization is Sp3 hybridization. Of course, again, going back to our atomic representation, what we're going to do is combine all 4 orbitals, the s orbital and the 3p orbitals, into 4 new orbitals that have the same energy. They are degenerate, we call them. And these orbitals have 25% S character and 75% P character. Again, we represent them the same way as we represent an sp and an sp2 orbital. Now, we saw with the sp hybridization, it's linear. With an sp2 hybridization, it's trigonal planar. With an sp3, we now have 4 orbitals, and we have to minimize electron repulsions when we fill those orbitals with electrons. How do we do so? How do we minimize electron repulsions when you have 4 orbitals that have electrons in them? The best way to do it is a tetrahedron, not a square planar, but a tetrahedron. So remember, in general chemistry we learned that when there are 4 electron groups around an atom, those electron groups separate themselves into a tetrahedral fashion. So methane must have 4 sp3 orbitals that are all equivalent, right? And again, the representation of carbon in this hybridized view, right? At an atomic view, the carbon has 2 electrons in the 2s and then 2 non-paired electrons in each of 2 p orbitals. But when we combine them now, all of the orbitals are degenerate, and so we get 4 unpaired electrons that each of them can form a sigma bond with a hydrogen. And so you get this picture of a carbon sp3 orbital, and this time I'll show the hydrogen 1s orbital. It's a lower in energy, again, because the principal quantum number 1 is less than that of a 2 sp orbital, right? And when we mix them, we get 2 new orbitals. Carbon donates 1 electron, the hydrogen donates another electron. It goes into the lower energy molecular orbital that we call the sigma orbital, right? And of course we have the sigma star antibonding orbital, and we know that the structure of these is actually very similar to ones we've seen in the past, right? The sigma is from the overlap of the in-phase areas of the sp3 orbital with hydrogen, and the sigma star is the overlap of the out-of-phase areas of the sp3 and the 1s orbital, creating that nodal plane in between them. And in terms of the entire structure of methane, if we denote carbon that has an sp3 orbital here, another also in the plane of the board, then we have an sp3 orbital coming out at us and an sp3 orbital going behind us. And each one of these is going to overlap with the 1s orbital of hydrogen here, 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 and here, right? So I have now the complete overlap of the 4 hydrogens together, and of course each overlap has a sigma bond where 2 electrons reside, and voila, I have my picture now, molecular orbital picture, that hybridized molecular orbital picture of methane. Now, one thing to denote is that energy difference between the atomic orbitals and the 1s orbital and the sp3 orbital, combining to give the molecular orbital, that sigma bond, uh, that energy difference is quite different, right? And we say that the carbon-hydrogen bond is 440 kilocalories per mole. This is a very strong bond, which means that alkanes typically are very stable and not very reactive. An important point that we'll see play out throughout the chapter.